So this lesson is regarding a sphere, and a sphere turns out to be probably the easiest of the three-dimensional figures because there's really only one dimension. To define a sphere, we are looking at a central point in space, and the sphere is defined as all the points that are equidistant from that center point, no matter what direction you go. So you see the cross-section in this image as a circle, but you could make that same circular cross-section through the center point in any direction that you wanted to. So there's an infinite number of circular cross-sections that are all the same with that same radius. So that same radius goes to all the surface points of the sphere. So the formula for the volume of a sphere is, as you see here, 4/3 pi r cubed. And the r part is the only input. So if we know the radius, we know the volume. And if we know the volume, we know the radius. So that's what we're going to be working with in this section. All right, so in terms of pi, the volume of a sphere with radius 6, if I put a 6 in for radius and work around the pi symbol, I end up with 288 pi inches cubed. Go to the nearest cubic inch. All we do is input that in the calculator, and we have our rounded version. All right, for exercise 2, a sphere has a great circle. The great circle would be the largest circle that goes around the sphere, and that would be, think of it like an equator on a globe. So the sphere has a great circle whose circumference is 95. Which of the following is closest to the volume? So if I look at the circumference formula, 2 pi r, and set it equal to 95, I can figure out the radius. Once I know the radius, then I can get the volume. That's all I need to know. So dividing by 2 pi, and remember on your graphing calculator, you have to group that in parentheses or divide twice. Radius comes out to, well, I didn't actually round it here. I kept it as 95 over 2 pi. Inserted that into the volume formula. By delaying this, I delay the rounding and get it to be more precise. If you do divide this on your screen first, just leave the decimal version on your screen before you enter it into the formula. And the volume comes out a little bit under 15,000, so the best answer is choice 4. Okay, so exercise 3. The largest sphere possible is placed in a cube with side lengths 8 each. So if I have a cube that's 8 by 8 by 8, and it's the largest possible sphere, that means that the sphere is touching all 6 faces from the inside. So if that's the case, then the diameter of the sphere going straight across the center must also be 8. That's why the radius of the sphere is 4. If I want to know the percent that the sphere occupies, I need to know the volume of both, the volume of the sphere and of the cube. So for the sphere volume, we put the radius in. For the cube volume, it's area of the base times the height. So the area of the base would be 8 squared times the height is a third factor of 8. So to get the percentage, all we need to do is divide the 288 by 512. Okay, so 52%, which to me looks a little bit lower than I expected. I expected it to take up more space, but there's a lot of space in the corners here, so that's why it comes out that way. All right, exercise 4, grain silo. And in this grain silo, we've got a cylinder, we've got a hemisphere. So if we can get the volume of both of those things, then we can figure out about how this corn packs into it at 16 pounds per cubic foot. In order to, so I have to know how many cubic feet there are before I can figure out how many pounds fit in it. So with the cylinder, we're going to do area of the base times the height. That's pi r squared times the height 15. That comes out to 1178. With the hemisphere, it works just like a sphere, except we have to multiply by half. So 4/3 pi r cubed for the sphere, and then half because it's a hemisphere. So you could simplify this and call it 4/6 or 2/3, but this all works out to be 524. And if you add them together, our total is about 1702. All right, so how many tons of corn can it hold if there are 2,000 pounds? Well, if I have 1702 cubic feet, I can multiply that by 16 to get the pounds, and then divide that by 2,000 to get the tons. So it's about 13.6 tons, which is quite a lot of corn. All right, exercise 5. Read through this problem and see what you can do with your setup to consider what is going to be involved here. All right, so looking through here, it looks like I've got I want to know how much ice cream is in this cone, because the final answer is how many calories is this treat. So I've got to know how much ice cream I have, and then I can add on the 85 calories for the cone. Well, when you get a scoop of ice cream, it fills up the cone. And then there's a mounded part here. And then if you get another scoop, you have a second spherical scoop of ice cream there. So we're going to treat it as if it's an actual sphere. So what I need to do is calculate a volume of a cone, calculate a volume of a hemisphere, and calculate a volume of a full sphere. So since all three of those are working off of the same radius, this shouldn't be too bad to do. So the ice cream component, we have a sphere on top, and we have a hemisphere sitting on the very top of the cone, and then we have the cone, right? So the volume of a sphere, we're going to do 4/3 pi r cubed, which would use the 4 for the radius. For the hemisphere, it's going to be half of that, so 2/3 pi r cubed. So again, 4 cubed. And for the cone goes 1/3 of what would be a cylinder, so 1/3 pi r squared times the height of the cone. Okay, so if I just put all of this into the calculator, just being careful to group everything, you want to make sure you group your fractions, or if you have a newer calculator, just it'll show up as a fraction, but the older ones you want to group them and add it all together. What we should end up with is a total for the volume of 603. Okay, now we look back at the problem. There are 237 cubic centimeters in a cup and then 320 calories per cup. So to convert this to cups, I would want to divide by 237, and that comes out to about 2.54 cups. And then if I want to get the calories, I want to multiply this by 320, and so that's approximately 812.8 calories. But then I need to add on the cone. So when I add on the cone, I get a total of 897.8 calories, which is a lot of calories, but it's an ice cream cone. So maybe you don't get that second scoop, and then you're going to take off about 270 calories off of that total. So that's how that would work out. We have it's basically a composite volume problem. It's a cone, a hemisphere, and a sphere.